Okay, so now we are on Unit 1, Day 5. We're going to talk about inverses. And then at the end, we're going to talk about parametric equations. So first off, learning target, I can find the inverse of a function given a set of ordered pairs, an equation, or a graph. So what is an inverse first off? So we should talk about that. An inverse is a function that undoes another function. So I like to think of the classic example is the function that converts Fahrenheit to Celsius. Okay, that'd be one function. And then its inverse would be the one that converts Celsius back to Fahrenheit. Totally different equation, but it undoes it. So if it was 10 degrees Celsius, convert it to Fahrenheit, and you say, okay, now convert it back, it should come back to 10 degrees Celsius when you come back. So it's a function that undoes another function. In the notation for this, the original function would be f of x. So its inverse then would be f, and then we do have x. It's a -1, which it's not an exponent. Some people think that's the -1 power. It's just a notation. It's just saying this is the inverse of f of x. So if that's your original function, this is its inverse, and vice versa. So, given the table below, we want to write in the inverse table. So if this is, maybe I'll put here instead of y, I'll put f of x. If that's f of x, then over here, f -1 of x, or the inverse of x, would be whenever I plug in 5, I would get 0. Because when I plug in 0, I get 5 here. So when I plug in 5, I should get 0 back. And when I plug in 3, I should get -1 back. And when I plug in -9, I should get 8. When I plug in -11, I should get 10. So you notice, basically all the x's and y's are switched. Okay, so this one's x's are that one's y's, and this one's x's are that one's y's. That means they're inverses. And that's exactly what this is saying down here. So the points A, B, and BA in the coordinate plane are symmetrical with respect, those are they're in each other's domain and range, so with respect to this line. So it actually, kind of got ahead of myself here. If you're graphing it, you can tell it's, you can graph its inverse quickly without ever knowing the function itself. So the points A, B, and BA are reflections of each other. So for instance, on here, pick a point, this might be like 1/2, 2. So that would be the point 1/2, comma 2. Over here is 2, comma 1/2. Okay, so that would be its reflection if you flip it over. And what they're saying here is, if you had a reflection about this line, so if I draw a diagonal line and reflect it, like we talked about reflection about the y-axis, well, this is reflection about that line. If I asked you to graph the inverse of this first one, it's actually that right there. It is its own inverse. Okay, so that one's kind of hard to look at, but if I flip all these points over, it would be the points on this side. Maybe an easier example might be, I don't know if this is super easy, but if I did say a parabola, I'll just do a parabola like this. If I were to reflect it about this line right here, take all these points and flip them across, and remember they're the same distance from it, it's going to look something like this. You can draw a sideways parabola there. So every point on here, whatever that distance is, it has another point that's the same distance from that line. So all these points get flipped over. Whatever this distance is, there's one over here somewhere. It should be a little bit wider like that. But it was up here, it got flipped that way. Okay? So now this one, take that line right there, and we want to reflect all of these points across that line. Now this one gets a little crazy. Actually, let's answer these points. I'm sorry, let's go down here and answer these. So we're supposed to determine whether the relation is a function. So given this, is the original one a function? Yes. Now graph the inverse. The inverse would actually end up being the same thing. It's the exact same graph. Because if you took this and flipped it over, flipped it like this, flipped it like that, it's the same thing. And then is the inverse a function? I can look at it and say, yes, it's a function. This original one, is that a function? Well, right here, my vertical line test, I'm hitting it twice in several places, so no, it's not a function. But now if I wanted to flip this, instead of having a line, we can kind of do this. This line right here is going, if it flips across, and that flips across, it's going to look something like this. When it reflects about that line, that's not absolutely perfect, but kind of. And this one, when this flips across and that flips across there, it's going to be, notice how it's close here and it's wide there. Well, it's going to be close, 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 and then wide here. So there is a reflection about that graph. And then this one here, it's kind of close on this side. It's kind of far away from that axis, so it's going to be the opposite way over here. Okay? So that red would be the inverse graph. And, you know, the asymptotes here, there's some asymptotes going through here. So is the inverse a function? That inverse, I can't hit it twice anywhere, so that one is yes, that inverse is a function. The original was no. So it's possible for the original and the inverse to be functions, and it's possible for them one of each to be, you know, one a function, one not a function. This original guy can hit it twice in several places, so it is not a function. If I want to graph this guy, and I'm reflecting it here, it's going to look more, let's see how white that should go down to 2. It'll look something like that when you reflect it. So you just flip it this way, right? So it is here, flip it over that way, flip all the points over. So graph the inverse now. Is the inverse a function? No, neither one's a function on that one. Okay, and then now this guy here, and think of that line going through there, and I want to reflect everything. So this would look something like, looks like my asymptotes are at 2 and -2, so that means my inverse is going to have asymptotes going this way at 2 and -2, so it's going to, and that comes down to about maybe a half. It's going to look something like this. Need to make that more blunt there. And then these would be going this way then. Okay, so is the original function a function? Yes, the original relation. I graph the inverse. Now the inverse. Now I can hit it several places or hit it several times in 2 places. Now I'm pretty good at doing this, the inverse stuff. It's not something I expect you to be that good at. You know, that didn't take me long to graph the inverse. It's something I've done before in my head. So some of you who are more artistic, you might be better at it. But just don't feel bad if you have trouble graphing the inverse. We're not going to ask you to do that, you know, on paper and pencil at all. But just to know that there's a diagonal line. There's a diagonal line there that it reflects. All the points reflect across. So if there's a point here, go across. There should be a point there on the inverse. Now, algebraically, doing this algebraically, this takes more time than anything. So to find the inverse of the following, find the domain and range of each. So are the inverses functions? So what we do is to find the inverse, we said that inverses switch each other's x and y. So that's exactly what I'm going to do. I'm going to take the y's and make them x's, and then take the x's and make them y's. Okay? And now to get a function, I need to get it at y equal. So I want a function of y in terms of x here. So I need to get y by itself. Now the best way to do this, when you've got a fraction on one side and not a fraction on the other, is to make both sides a fraction and then set cross products equal. So I'm going to have 1 times y minus 2 equals x times y plus 3. Now I do some distributing. So this will be xy plus 3x. I got 2 terms that have y's in them and 2 that do not. I want the terms with y's in them on the same side. I'm going to bring the xy to the other side, so y minus xy, and I'm going to bring that 2 to the other side, so 3x plus 2. Let's see. And now these both have a y in them, so I'm going to factor a y out, so that would be 1 minus x equals 3x plus 2, and then divide by 1 minus x. So now I got y by itself. That's the inverse. So, and if you want to take out the y, you can put f negative 1x in its place. So the inverse would equal this. So here I've already switched the x and the y's. Bring the 2 to the other side, so divide by 2. Take the cube root of both sides. So I'd have y plus 3 on the right side, and then over here I'd have, and you could just leave that as a cube root of x divided by 2. Subtract 3 over, so the cube root of x divided by 2 minus 3 would equal y, which is also the inverse. So we just put the notation as the inverse. So this would be the inverse. And this guy here, switch the x and the y, and then start plugging away, trying to get y by itself. So bring the 5 over, so x minus 5 would equal this. Then I'd get rid of that 6 next, so multiply the 6 over. So it'd be 6x minus 30 would equal 2 times y plus 9, and then minus 1. Add the 1 over. So that would be 6x. And if I added 1 to that, it would be minus 29 equals 2 radical y plus 9. Divide by 2. And then you could square both sides. So that would be 6x minus 29 over 2 squared equals y plus 9. So subtract 9 from this side. I'm going to save some space and just subtract 9. Sorry, I got a little sloppy at the end there. So that was if I gave you one function, I want you to find the inverse. Here I'm going to give you two functions and say, are they inverses? So we can use composition to find out if they are inverses. So how we do that is, if they're inverses, then f of g of x will equal x, and g of f of x. So both ways when you compose them, you get x. So we're trying to say, we'll put a question mark there, does that work? So f of g, I'm going to go a little fast here, says to take function f and plug g in for it. So wherever I see an x and f, I'm going to put 3x minus 6 divided by 2, and do some simplifying here. So the 3's would cancel, the 2's would cancel, x minus 6 plus 6 would equal x. And then g, so I'm going to take the x out, I'm going to put 2/3 x plus 6. So on top here, I got plus 6 minus 6, that would be gone. And I've got, if I multiplied this, right here, 2/3 times 3, that'd be a 2, and then, or 2x, and then 2x divided by 2 would be x. So this one, showed this, so yes, we already knew that, said it was, so show using composition. So same thing on this one, maybe to shorten the video up, I'll say, try that one on your own. It says show using composition that they are. I guess it says if, never mind, it says if. So this one, the answer is yes, so try that out on your own. The parametric equations here now, this is just another way to define functions, is to define both elements in terms of a third variable, t, and then when we do that, that's called a parameter. So consider this, say x equals t plus 1 and y equals t squared plus 2t. And we're supposed to evaluate from -3 to 2. So what we're saying is, if t is -3, that'd be -3 plus 2 is -2, so that'd be your x value. And you could go through and do all the x values first if you want, just going to add 1 every time, so it'd be -1, 0, 1, 2, and 3, because 2 plus that 1 is 3, and so on. Now the y's you get by taking t squared plus 2 times t. So t squared would be 9 plus 2 times -3, so that'd be a 3, because this would be a 6. Again, t squared would be 4 plus 2 times -2, so that'd be 0. -1 squared is 1, plus 2 times -1, so that actually would be a -1. And then 0, 3, and 8, I'm kind of fast forwarding. And then it says we want to, so there we fill out the table, evaluate the functions. Now find an algebraic relationship. So we want to figure out, how does y and x, what's in common with them? So what I'm going to do is I'm actually going to substitute. I'm going to solve one of these for t. So you got x equals t plus 1. I'm going to bring this over, so x minus 1 equals t, and then plug that in for all the t's down here. So y equals x minus 1 squared plus 2 times x minus 1. And see, now we have a function. Okay, so y equals, and we got x's on the other side. That's going to be my relationship between x and y. So y equals x squared minus 2x plus 1 plus 2x minus 2, if I'm distributing all this. So y equals, x squared minus 1. And if you graph that on your calculator, you need to graph on your calculator because it's a parabola down 1. It's going to look something like that.